Hello everyone. In this lesson, we will try to understand how the conductivity or the resistivity of a conductor depends on temperature. So for that, we'll start with the expression for resistance. Resistance of a conductor is uh, directly proportional to the length of the conductor, and it is inversely proportional to its area cross section, as it is given by this expression here. And this term is the proportionality constant, and it is called the resistivity of the conductor. So from this equation, it is apparent that increasing length of a conductor increases its resistance, and increasing area of cross section of a conductor decreases its resistance. So therefore, the resistance of a conductor depends on its length and area of cross section. Now suppose if the question is like two conductors, one is suppose copper, another one is iron. So which one has more resistance? So normally we tend to think that copper is a better conductor than iron. So the copper may have, say, like less resistance than iron. But here the answer depends on the dimensions of the conductor as well. So we may have a situation where we have a long copper conductor and a short iron conductor. So in that case, iron may have a less resistance than copper. So this term resistivity, which is defined as the resistance offered by the conductor of unit length and unit area of cross section. So from the definition itself, this resistivity, it does not depend on the dimensions of the conductor, rather it depends on temperature. The SI unit of electrical resistivity is ohm meter. So for a conductor, a resistivity is given by this expression. So rho, which is the symbol for resistivity, rho equals to m divided by n e square tau. So where m is the mass of the free charge carrier. So here the free charge carrier is electron. A density of the free charge carrier, E is a charge of the electron, and tau is the relaxation time. So the reciprocal of resistivity is conductivity. So the expression for conductivity is the reciprocal of this expression, which is given here. Now next we will try to understand how the conductivity of a conductor depends on temperature. So when we increase temperature, the value of N increases, or the free charge carrier density increases. Now why and how? Because by increasing temperature, more electrons, they move from valence band to the conduction band. In simpler word, more electrons, they move from bound state to the free state. So it is because of this reason the value of N increases with temperature. Relaxation time. So this relaxation time is the average time interval between two consecutive collisions. So when we increase the temperature of a conductor, the collision frequency increases. So because of the increase in the collision frequency, the average time interval between two consecutive collisions decreases. E is the charge of the electron and m is the mass of the electron. So charge and mass, they are independent of temperature. So we have a situation here, by increasing temperature, the value of N increases, whereas the value of tau decreases. So what is the net impact here? So for that, we need to look at the dynamics of a conductor. For a conductor, the value of N, or the free charge carrier density, is very high. So it has the range of around 10 to the power 28 meters per meter cube. So because of that reason, uh, increment in the value of N has less significance than the decrement or the decrease in the value of relaxation time for conductors. Or in another word, the impact of decrease in the value of relaxation time is much greater than the impact of the increase in the value of N. So it is because of this reason, for conductors, increasing the temperature decreases its electrical conductivity. For semiconductor, we have exactly the opposite situation. For semiconductors, the value of N is relatively less, number one. Number two, with increase in temperature, there is huge increment in the value of N. So it is because of this reason, for semiconductor, when we increase temperature for a semiconductor, its impact in the increase in the value of N is much greater than its impact in the decrease in the value of tau. So it is because of this reason, for semiconductor, conductivity increases with temperature. Now we have this expression here. So R equals to R naught 1 plus alpha T minus T naught. Uh, okay, so T naught is some reference temperature. So R naught is the resistance of that material at that temperature. So uh, I find this equation very beautiful because of its underlying principle. The principle is if we know the resistance of a material at some reference temperature, then we can find the resistance of that material at any given temperature T. So if I replace R by rho L by A, so we have the expression in terms of resistivity. The principle here also remains the same. And that is, if we know the resistivity of a material at some temperature T naught, at some reference temperature T naught, then we can find the resistivity of that material for any temperature T. So provided we know the value of alpha. So alpha is defined as a temperature coefficient of resistivity, and the value of alpha is different for different material. So I regard this alpha as the protagonist of the whole situation here, because how the resistivity of a material depends on temperature is defined by the value of alpha. So I've explained that in this slide. Case 1, when alpha is positive. So when alpha is positive, increase in temperature increases resistivity, or decrease in temperature decreases resistivity. So we may have two cases here, alpha positive with large value and alpha positive with less value. Okay, so before that, I have used some notations here. The students are advised like not to use this type of notations, so I have used it only for simplicity. So as you can see here, I have a small arrow and I have a larger arrow here. So the meaning of this expression of my notation is, if there is increase in temperature, then there is a relatively larger increase in the value of resistivity for the material. Similarly, when there is a decrease in temperature, there is a relatively larger decrease in the value of resistivity. So when alpha is positive, so we have these situations here, and this is the case with metals. Similarly, when alpha is positive with less value, a relatively increase in temperature results in a relatively smaller decrease in the value of resistivity, or a decrease in temperature results in a relatively smaller decrease in the value of resistivity. So this is the case with alloys. Similarly, in case 2, when alpha is negative, increase in temperature decreases resistivity, or decrease in temperature increases resistivity. So when alpha, again we have two cases here, alpha negative with large value and alpha positive with alpha negative with less value. So when alpha is negative with large value, so here also uh, increase in temperature results in a relatively large decrease in the value of resistance for the material, and vice versa. When alpha is negative with less value, increase in temperature results in a relatively less decrease in the value of resistivity. So as we can see from these two cases, the value of alpha decides how the resistivity of a material varies with temperature. We have this table here. So this table shows the values of alpha for conductors and semiconductors. As expected, for conductors the values are positive, and for semiconductors the values are negative. And also, alloys, they have less value of alpha than metals. Now with this we have come to the end of this lesson. One last question: which material should be used for making standard resistors? So remember, for standard resistors, we need material whose resistivity should not change much with temperature. So for that, it takes us to this slide here, a small positive value of alpha. So in this case, even if there is a huge change in temperature, the change in resistivity is relatively less. So therefore, alloys like constantan and manganene, they are used for making standard resistors.